All right, so this is just a continuation of the last video. I'm going to work on rate reaction mechanism and rate limiting practice. Just a couple of examples because I want you to make sure that you're very prepared for class on Monday since we've lost a few days. So what I want to show you now is that same reaction we've been working with, and I just want to break it down for you. I know I did kind of give you a little bit of an idea of it on the last video, but what I want to show you is that there's always going to be a slow and a fast step when you are looking at your elementary steps. Again, if this is on the AP exam, they're going to give you that information. Okay, so they will tell you that this one here is a slow step, meaning that the two NOs, when they collide, it's going to happen fairly slowly. And then they will tell you that this is the fast step. Okay, they are going to put that in parentheses or in italics. They're going to show you the slow and the fast. They will, maybe even in brackets, but they're going to show you the slow and the fast step. They're not going to expect you to guess because it's not something that you're going to have to memorize. Okay, and then what you'll do, the same way we just showed rate laws. Okay, so when I had, where's my paper? There it is. Okay, so I just showed you for any elementary step, whatever the coefficient is, you're going to have K is equal to the concentration of your reactant, and then you're going to have the coefficient is going to become a subscript, superscript, I don't remember which one that is, but y'all know what I mean. All right, so very simply for step one, we're always going to, when we write our rate law, rate is equal to, and I put the little 1 there so I know that is for elementary step 1, and we've already written this. I just want to show you one more time. Okay, and that, of course, the coefficient is going right up here. And then for step 2, the rate of step 2 is going to be our rate constant for reaction 2, NO3, and there's no subscript, superscript, whatever you call it there, and the rate of CO. Now, very simply, I am going to say that my rate here is not this one, because that isn't limiting my reactant, right? My slow rate is going to limit the rate, so that means it can't go any faster than this. So this is as fast as it can go, so this will always be. All right, so the rate of the overall reaction is always equal to the rate of the slowest elementary step. Another thing I want to point out is notice that CO, if I add any CO to the overall reaction, it's not going to affect the rate because it's to the 0th order. Okay, so no matter what I do here, even though CO is in my overall reaction here, NO is what we call an intermediate. So it cannot be in the rate reaction. We'll get to that in just a moment. But CO is to the 0 order. It is not going to affect my reaction at all. No matter how much concentration I have in it, it does not matter. So this must be to the 0th order. So this is where it gets a little bit tricky and, in my opinion, kind of interesting. So we have NO and O2, and when we add those together, combine them, collide, we have NO2, but this is one of the reactions that has elementary steps. So, of course, what I've told you before is they will give you the elementary steps. Notice here that we have arrows going backwards and forwards, okay? So what this means is this is called an equilibrium equation or equilibrium reaction. Equilibrium, I believe, is unit 7, okay? We will be getting to that, maybe it's unit 6, I don't know, but we'll be getting to that. Okay, so this very first step, step 1 of our elementary equations, is reversible. Okay, it is also our fast reaction. Okay, our fast reaction is a reversible reaction, meaning it could go backwards and forwards. When it's in equilibrium, that means it goes backwards and forwards, same rate. Okay, and this is also going to tell us that this is our slow reaction. The problem with this is, and I'm going to show you that, step 1, our rate, the rate of 1, okay, I don't know why I did put the O2 there. I think maybe I am crazy. No, I didn't. I just didn't write it. All right. Guys, I have the wrong thing written. I apologize very much. So, step 1, I'm sorry guys, K1, y'all know I can make mistakes too. There's our step 1, okay? So that is the rate for step 1 right there. Now, it is the forward reaction, okay? So that is the step 1 for the forward reaction. That's why I didn't have it down, I'm crazy. All right, and then the rate, because I'm making all my stuff crazy. So then our rate for our reverse reaction, meaning that this can also be a reactant, okay? So the rate for the reverse reaction, this is how I'm going to write that now. Of course, I would write it next to it, but I don't have a lot of room anymore because I messed up. Okay, so K1 for the reverse reaction. And I'm going to put a K negative 1 because it's reverse. That's going to be NO3. Okay, because my NO3, I'm finding that this is disappearing when I go backwards. So this arrow matches that one, and this arrow matches, that one. All right, so now I need to look at my elementary step 2. Let me make sure I got this right. I have a little, all right, yeah, because that one's easy. All right, so the rate of 2, y'all making all kinds of mistakes now. It's late, it's Friday. All right, is we just have our NO3 and our NO. And remember what I told you on our last, I don't know if it was the last video or the last, yeah, I think it was the last video. Our intermediates cannot be in our rate law. And unfortunately here, NO is in our equation, but NO3 is an intermediate. It's right here. We cannot have it in our rate law. So that presents a problem. So what we're going to have to do at this point is actually, is this on my next paper? Probably not. I don't. All right. So we're going to have to work this out in a very interesting way. And let me show you that. So what I need to do, and I'm sorry this is taking so long, guys. I just wanted to show you this. So what I have to do here is take my rate of my reverse and my rate of my forward. So what I do with that is say that the rate of my reverse is equal to the rate of my, that's the rate of my forward, sorry, is equal to the rate of my reverse. Okay, and so once I have that, I'm going to divide both sides by K negative 1. Okay. This crosses out. So now I know that NO3 is also equal to this whole equation. So my actual rate law, okay, because I know my rate law is going to be my slowest step, meaning it has to be this, right? But I can't have this in my final equation. This is my slowest step, but I can't have this in my final rate law. I can't have it because it's an intermediate. So what I have to do is what I'm doing right here. I apologize for going back and explaining. I just want to make sure that y'all know. So the rate law for this, I'm going to take all this here because all this is equal to the NO3, and I'm going to fill that in. Okay, so my rate law is equal to K2, and then multiplied by that whole big thing, which is K1 over K negative 1 times the NO, the O2 concentrations, and then I just fill back my NO right there. Okay, you see how I took this whole thing and I put it right there. Okay, and that right there is how you are going to do it. Okay. So remember, just real quick, rate law is determined by chemists through experimentation. It is not something that can be done or predicted. All right, hopefully this helps.